So when scientists looked at the periodic table and the way that the elements are arranged, they also noticed that there were really clear trends in terms of the atomic size. As you went left to right across the table, the atomic size decreases, whereas as you go down the table, the atomic size increases, and the trends are really clear. Maybe there's a few outliers occasionally, but overall, the trends were very consistent. And there's a couple explanations for these. Probably the easiest one is, why does the size increase as we go down the table? Well, that can be assigned simply to the fact that we are increasing n, or the principal quantum number, or the energy level, as we go down the table. Remember, we're getting to a new energy level of orbitals that we're filling, and each new energy level is farther away from the nucleus. So if the electrons are farther away from the nucleus, then naturally the radius of the atom is going to increase. So that one's very clear, but then there's the question of, why does the atomic radius decrease as we go left to right across the table? Why does it decrease horizontally? To answer this question, we have to look at something that's known as the effective nuclear charge. And it's given this abbreviation Z subscript effective. The effective nuclear charge is the charge that the valence electrons, the ones in the very outermost shell, actually feel. So remember, the nucleus has the protons, and so it has a certain charge just based on the number of protons that are present. So we could, if it's got 2 protons, then we would give it a +2 charge in the nucleus. If it's got 45 protons, it's 45 in the nucleus. But the outermost electrons, the valence electrons, don't necessarily feel all of that full charge from the nucleus, because the core electrons provide some kind of shielding or blocking of some of that charge from the nucleus. And we describe that in this equation here, where the effective nuclear charge is described as Z, which is the actual nuclear charge. It's simply the number of protons in the nucleus. And S is the shielding factor. And it's very approximately equal to the number of core electrons. Now, there are more detailed equations, and there's quite a bit of study on being able to measure the actual value of S. But for our purposes, for this class, we can simply approximate S as being equal to the number of core electrons. And so we can see that for even a simple element with not anything past helium, which will have core electrons and valence electrons, the valence electrons are not going to feel the same measure of nuclear charge as the core electrons will. And we can think about this in an illustration here. If we have a light bulb that's out on a stand and there's nothing blocking it, then the amount of light that comes to your eye is very bright. But say we put a frosted piece of glass in front of that. You still see a lot of light, but you don't have the same intensity. You can even think about this just in terms of an actual light bulb. So most light bulbs have frosted glass on them, but you can sometimes find old incandescent light bulbs that have clear glass, and you can see the filament itself very clearly. And this is essentially what's going on, where your eye is acting as the valence electrons, and the frosted glass is the core electrons. So the amount of light that you see is less than the amount of light that's actually being generated from the nucleus or the light bulb. So how does this work then in a couple examples? Let's just take period 2, the second row, and just do a few examples. So let's start with lithium. Its atomic number is 3. It has 3 protons, therefore, and so Z is just 3. It has 2 core electrons because its electron configuration is 1s2, 2s1. So 2s1, that's the valence electrons, and the 1s2, those are my core electrons. So it has 2 core electrons S is therefore approximately equal to 2. What that means is that the actual charge that the valence electron feels is actually only +1. Even though there's a total of +3 in the nucleus, that valence electron only feels a positive charge of about +1. Now, as we go across the periodic table, let's just move over one to beryllium. It's got 4 protons, so Z is equal to 4. It still has the same number of core electrons, though. Its electron configuration is 1s2, 2s2, so it still only has 2 core electrons, even though it's got 2 valence electrons. So since S is approximately equal to the number of core electrons, S is still just 2, which means that the valence electrons for beryllium feel a +2 charge. So they feel more of a positive charge than the valence electron in lithium. As you move even farther over to carbon, Z is now 6, that's the number of protons, but the number of core electrons still hasn't changed, it's still 2. And so the effective nuclear charge that the valence electrons in carbon feel is +4, so more than beryllium or lithium. Now, because there's an attraction between positive charges and negative charges, then this explains this increase in effective nuclear charge as we go left to right across a row, explains the decrease in atomic radii, because there's that attraction between positive and negative charges. If the positive charge is great, if the effective nuclear charge that is felt is greater, it's going to hold those valence, it's going to attract those valence electrons closer. So it's going to hold them closer to the nucleus, and thus the atomic size will be smaller. Now let's take this and extend it a little bit more and talk about trends in ionic radii. So we've described why there's the trends in the neutral atoms as we go across the periodic table. But what does it look like when we have ions, either a cation where we've lost valence electrons or an anion where we've gained valence electrons? Well, cations are smaller and anions are bigger than their neutral parent atoms. And I think we can make some sense of this. If the atomic radii is the distance from the nucleus to the valence electrons, if a cation, like lithium, for example, if it's just lost its only valence electron, then certainly now the distance is just the nucleus to the core electrons. That's certainly smaller than what it was previously. So cations, because they've lost electrons, their size is smaller. Also, there's a small factor where valence electrons actually do shield each other to some extent. And so if you lose valence electrons, then there's less of that shielding as well. So there's some impact there in cases where, if we had a case where we lost some but not all of the valence electrons. Anions, on the other hand, are larger. Well, as I said, valence electrons actually do shield each other a little bit. And so if we have more valence electrons, then there's a little bit more shielding. So the effective nuclear charge goes down slightly, and thus the valence electrons are not held as tightly. So the distance is larger. We can look at that here just as comparisons. So the neutral lithium atom has a radius of 1.28 angstroms, but the cation, where we have lost the only valence electron, now we have a significantly smaller ionic radius compared to the neutral atom. Also, because the effective nuclear charge increases left to right across the periodic table, then the sizes of the ions also follows that same trend. The effective nuclear charge for beryllium, remember, we determined that to be +2. Well, the ion of beryllium then those electrons feel a larger charge than the ones for lithium. And now we're mostly talking just about the attraction between the core electrons and the nucleus. But I have more protons, larger charge, And so those electrons, even the core electrons, are held more tightly, and the size of the ion is smaller. And you can see that here just looking at lithium, the lithium ion versus the beryllium or boron ions. And then sort of the converse is true. So in cases, if we compare oxygen and fluorine here, fluorine only gained 1 valence electron to go to F minus. It's certainly larger than just fluorine by itself, but oxygen gained 2 valence electrons. Also, the effective nuclear charge of oxygen has 1 less proton than fluorine, so it's going to have less of a nuclear charge and thus less of an effective nuclear charge. So those outer electrons are held even less tightly. So let's take these concepts and expand on it a little bit. Rank the following ions in order of decreasing size. So we have the magnesium 2+ ion, we have aluminum 3+, we have oxygen 2-, sodium plus, and F-. Well, if we look at each of these and write out the electron configuration for each of the elements, or each of the ions, what we will find is that the electron configuration for all of these ions is actually the same. It's helium, then 2s2, 2p6. So the number of valence electrons, if we want to think about it this way, the number of valence electrons for all of these is going to be 6 valence electrons. The number of core electrons will be 2 for all of them. However, if I look at the effective nuclear charge, I notice that they don't all have the same number of protons, and thus they won't all have the same effective nuclear charge, and the valence electrons will not feel the same pull. So if I simply look at the atomic numbers for each of them to figure out what Z is, and I'll just pull up my periodic table really quickly to get the atomic numbers. So magnesium, for magnesium, its atomic number is 12. So Z equals 12 for magnesium. For aluminum, Z equals 13. For oxygen, I'll just sort of draw this over here. Oxygen, its Z is only equal to 8. Fluorine, Z is equal to 9. And sodium, Z is equal to 11. So if I go through then and simply calculate the effective nuclear charge for each of these, Z effective is equal to Z minus S. Well, S is just the number of core electrons. So S here is 2 for all of the cases. But Z is different, and so we can see that the ions that have the largest number of protons, that have the largest value of Z, are going to have the largest effective nuclear charge. So aluminum has 13. So 13 minus 2, it will have a plus 11 effective nuclear charge that those valence electrons feel. This is for the aluminum, 3+. Magnesium, on the other hand, 12 minus 2 is going to feel plus 10. For magnesium, 2+. And then so on and so forth. So for sodium, that will go down to 11 minus 2 is plus 9 for sodium. For fluorine, 9 minus 2 is 7. And then for oxygen, 8 minus 2 is 6. So oxygen 2 minus. If I look at each of these, I can see that the larger the effective nuclear charge, the more tightly bound those valence electrons are. And thus, the smallest ion will be the aluminum 3+, whereas the largest ion will be the oxygen 2-, the O2-. So in order of decreasing size, we can draw them like this. Now, I'll just clear this ink. And let's take just a look at it. We can see these actual values here. So aluminum 3+ is at 0.68 angstroms, and oxygen is up at all the way up at 1.26 angstroms. Now, there's one last point I'd like to make with these. So we noticed that the electron configuration for all of the ions was the same. The number of protons is different, but the number of valence electrons and the configurations of those ions were all the same. In any case that you have, anytime you have different species that have the same electron configurations, even though they're different elements, we refer to those species as being isoelectronic, meaning simply that they have the same number of electrons. And so all 5 of these species would be isoelectronic. So hopefully that's helpful in how we use effective nuclear charge to talk about atomic size and trends in atomic size, and then also trends in ionic size.